give us a lecture on quantum loop gravity on behalf of the Science Hub and Student Life and Brown College in general. Let's hear it for Dr. D'Elia.
So today's talk is about loop quantum gravity, which sounds probably pretty esoteric. I'm going to try and relate it to stuff that makes sense to you. Loop quantum gravity is inherently very mathematical, but I'm going to try and keep you don't have to solve any equations while you're watching this presentation. There will be equations, but you can just look at them, and I'm not going to ask you to understand anything other than just appreciate them. Okay, so loop quantum gravity. We're going to start the story back a little over 100 years ago. I just got done saying it, there's no math, and then look at all that. We're going to start the story of 130 years ago, 140 years ago. Classical physics, at the end of the 1800s, the 19th century, we thought we had it figured out. Physicists thought that they were on the verge of putting final touches on a perfect understanding of the physical world. And we had Maxwell's equations, which are in the upper left-hand corner, that describe electricity and magnetism. In the upper right-hand corner, we have Newton's law of gravity, which explains why we are stuck to the Earth, and the moon orbits the Earth, and the Earth orbits the sun. Below that, we have one of the fundamental laws of thermodynamics, the second law of thermodynamics, expressed in one of its forms. And on the lower left here, we have Bernoulli's equation, which describes how fluids work. So again, I'm not going to ask you to understand any of these. These are just a collection of all the physics that summarize the known physical world pretty much at the end of the 19th century. So we thought we had it all figured out. And Lord Kelvin said that past this point in the 20th century would just be filling in little minor details. That boy was he wrong, because right at the turn of the 20th century, we made two major discoveries. One was an extremely impressive insight by a gentleman named Einstein. Another one was a very surprising solution to a vexing problem for physicists by a guy named Max Planck. The guy on the left, Max Planck, he is sometimes considered the father of quantum mechanics or quantum physics. And Albert Einstein is the father of relativity. And there's two versions of relativity, special relativity and general relativity. We're going to talk mostly about general relativity today. But I use Max Planck to represent the quantum physics pillar of modern physics, and Einstein to represent the general relativity or quantum gravity. Well, actually, later on it becomes quantum gravity. The gravity and general relativity pillar of physics. So with these two new physics, these two new areas of physics, we discovered that the world was much, much stranger and much, much different than we had thought previously, in just like 10 or 20 years before in the late 1900s. Let me talk a little bit first about Max Planck. Max Planck was trying to solve a problem in thermodynamics. Thermodynamics has to do with the temperature of objects and how heat transfers from one object to another. It was something called the ultraviolet paradox, or the ultraviolet catastrophe. When you calculate the radiation given off by a body, every body gives off radiation. Our bodies give off radiation, stars give off radiation. And the radiation all depends on the temperature of your body, how hot your body is at the surface. Stars typically are around a few thousand degrees Kelvin. We're, a few thousand degrees centigrade. Our bodies are a few tens of degrees centigrade. Whatever the body is, it gives off a characteristic amount of radiation at every wavelength. And this is called, for reasons I'm not going to go into right now, it's called the black body spectrum. The problem was, the mathematics to describe the radiation given off by an object was giving very strange results. It was giving us this curve right here. If you look at this curve in the middle, if you tried to calculate it classically, you would see that the amount of energy given off would at short wavelengths, at high frequencies, which is short wavelengths, very short waves. The shorter the waves are, the more radiation a body will give off. And it went to infinity. You can see that little curve, it's curving, it's going to infinity. So our mathematics at the time was implying that all objects, no matter what temperature they were giving off infinite amount of energy, which we know isn't true. Well, it took a strange but very impressive solution from Max Planck to come up with the curve that we actually measure. This curve, you see the curve that doesn't go off to infinity, the one that has a little hump there, that's the curve that he got when he made his little assumption. His assumption was that energy is carried not in continuous amounts, but in what are called discrete quanta, that a wave of electromagnetic radiation can give you 1 unit of energy or 2 units of energy, but not 1.5 units of energy. That electromagnetic radiation carries a specific amount of radiation, and if it interacts with matter, or if matter generates it, there's only certain amounts of energy can give off. In this quantization, or going from any old value to just particular, what we call discrete values, changed the picture. It was very strange. At the time, he said he didn't know why it was this way. He just introduced it as a little mathematical trick, and it worked. Later on, Einstein actually helped us understand why it worked, where it comes from. So it has to do with the fact that objects, quantum mechanical objects, atoms, molecules, things that are smaller than an atom or smaller than a molecule, behave in a much different way than we expect, or we've seen in classical physics. We'll talk more about that in just a minute. The other observation, or pillar of physics, was Einstein's general relativity. In 1905, he came up with something called the special theory of relativity after studying Maxwell's equations. I showed you on the previous slide, there was a set of 4 equations. Those are called Maxwell's equations that describe electricity and magnetism. Well, he did a little thought experiment, and it turns out that if you could travel at the speed of light, that the laws of physics would depend on your point of view, would depend on how fast you're moving. And that was sort of unsatisfactory. So he decided that, well, rather than change the laws of physics and make the laws of physics depend on how fast and what direction you're moving, he said, well, I just can't travel at the speed of light. And that was actually turned out to be the right solution. That was special relativity. Later on, he generalized his result to general relativity. General relativity turns out that all the laws of physics are true, not only independent of what direction you're moving or how fast you're moving, but also whether or not you're accelerating, whether you're falling or you're in a car accelerating. The laws of physics still remain the same. So it sounds like a tiny difference between just moving at a constant speed and moving at an accelerated speed. But what Einstein discovered was, even moving at an accelerated speed, if you assume, if you assume that the laws of physics are true even when you're accelerating, then you have to come up with general relativity. General relativity describes gravity. It was basically the first deep insight into gravity since Newton, a few hundred years before, came up with the universal law of gravitation. All right, let's talk about quantum mechanics. I said I was going to talk for a minute or two about quantum. This is the physics that applies to very, very small objects, much smaller than we can see. Atoms, the components of atoms, electrons, protons, and even things that we can even subdivide protons and neutrons up into smaller particles called quarks. And there's actually other objects besides these that are made up of quarks, other strange particles. There's a whole zoo of particles. Quantum physics describes how these particles behave on a very, very small scale, much smaller than we can see. And it turns out that the quantum world is very, very strange. The idea that you can measure something and get a value, or that something has a particular value. Say I measure the temperatures. Let me talk about the speed of an object. If I want to measure the speed of an object, that's something you would think, okay, there's an object out there that's moving at a certain speed, and whether or not I measure it, that speed is what it is. But it turns out in quantum mechanics, for very small objects, that they're moving, but they're not moving with a single speed. They're moving with what's called a distribution of speeds, or probability distribution of speeds. And it turns out that it's not just imperfect information. It's not that we don't have an instrument that's precise enough to measure the speed of some quantum object, whether it's a particle or a wave. Actually, waveable is what we call them in quantum mechanics. It's not that we're not able to come up with a piece of technology that can measure. Someday someone's going to be smart enough to come up with an instrument that can measure the exact speed of this arbitrary object I'm thinking of. It's that we'll never be able to do it because it's something inherent in the nature of the object itself. The object itself is moving with a distribution of speeds. How can a single object be moving at more than one speed? Well, that's one of the mysteries of quantum mechanics. That quantum objects behave as if they have a distribution of properties, not a single value like speed or energy. Now, when you go to measure it, when you go to interact with an object, a quantum mechanical object, whether it's an electron or a photon or something like that, you will get a single value. And that value is based on the probability distribution at the time of the interaction. But until you actually measure it, until you actually interact with that particle, it behaves as if it has a range of values, or maybe a what we call a spectrum of values. And that determines the property. You can't say that it has this value or that value. It's not moving at 1 mile per hour, or 10 miles per hour, or 30 miles per hour. It's moving with a certain probability at 1 mile per hour, another probability at 10 miles per hour, and so on. And until you actually interact with it, you can't say that it has a particular value. It doesn't even have a particular value. It just has a distribution of values. When you interact with it, that quantum mechanical object, we say collapses into a single state that has a single value. Very strange stuff. What are we talking about here? Actually, we really don't know yet. You don't have to see attention to that. You don't have a clicker? It just clicked on that.
So I don't think it's not working.
Did I go to it?
Yeah. There you go.
Okay. So thanks. No, okay. And then the other that was quantum mechanics. The other pillar of modern physics is general relativity. This describes objects on very large scales. So what forces predominate on very large scales? There's only one force that predominates on large scales, and I don't know what it is. Gravity. Gravity is the only force. There's four fundamental forces. There's four forces of nature. Anything that's a force can be broken down into one of these four kinds. The only kind that works on very large distances, like distances, say, planets, galaxies, stars, that's gravity. And general relativity describes how forces act, or how objects act on large distance scales. So basically, general relativity is a theory of gravity. It's a deeper theory of gravity than we had with Newton. Newton simply gave us an equation of the force between two. He didn't say anything other than this is the force between two particles with mass. If you want to know anything more than that, that's basically where it ends. That's the given. General relativity gave us a much deeper insight into how objects move, a way of describing how objects interact with each other. And it turns out that classically we think of space and time as two different things, right? Space, we can move through space. I can move left, right, forward, backward, up, down, if I have a ladder or jump. But time, can I move back and forth in time? No, time is something different. Time is not a spatial dimension. It's another aspect of physical reality. What is, well, that's a whole lecture in itself, what is time? But it's something that we move in one direction through. We move through, at least our experiences, we move through time in one direction. Well, it turns out in general relativity that you can't think of these as separate things, that your motion through space also determines how you experience time. If two different people are moving through space at two different velocities, they're going to experience time in different ways. One person's clock is going to move faster than another person's clock if that clock is moving with them, if they're carrying a clock with them, or if they look at their watch. The person moving faster their watch is going to move slower. It's very strange, but it's the consequences of general relativity. If it's actually possible for humans to go to other stars, if we could go fast enough, if we wanted to go to the nearest star, which is Alpha Centauri, it's about 4.5 light years away. We'll ignore the fact that we don't have enough energy to get a person there. But if we had a spaceship that had enough energy to get us there, at conventional speeds, it'd take about 70,000 years. Okay? If you could go close to the speed of light, it would take about 4.5 years. But if there was a person traveling to Alpha Centauri on a spaceship that was traveling close to the speed of light, they would actually experience, it might take, depending on how close they're traveling to the speed of light, it might take them a day, it might take them maybe 2 days. Okay? This is due to the fact that they're moving so close to the speed of light. This is a consequence of relativity. It's a special case of relativity called special relativity. But it's very strange. Space and time, the fact that they don't act independently of each other, that space depends on time, time depends on space, means that we have to take a completely different view of the world. Space-time is also affected by mass. And what does that mean? Well, objects have mass. It's a physical property of objects. How can we think of this? Well, the way we usually visualize this is you think of space and time, empty space and time, is like a flat sheet. And if you put an object inside of space and time in some coordinate system, what it does is it causes a little indentation in that sheet. And so if you put another mass somewhere else, it will feel that indentation. It will roll into the indentation of the other object. Okay, so that's a sort of just a toy model way, an easy way to visualize the concept of space-time. Space and time are not separate. They're the same thing, and they act like a sheet or a fabric through which you can move. And it bends, it warps, and that warpage is caused by mass. This is general relativity, which basically describes gravity. Okay, well, so we have, I said earlier, 4 fundamental forces. The 4 forces we experience in nature. Everything can be broken down into one of these 4 forces. The first 2 you may have heard of. Everyone's heard of gravity. Probably most of you, or a lot of you at least, have heard of electromagnetism. There's 2 other forces that were discovered in the 20th century, the strong nuclear force and the weak nuclear force. This has to do with forces inside the atom. The strong nuclear force basically holds the protons together inside the atom, because if you know a little bit of electromagnetism, protons are all positively charged, and they don't want to be close to each other. Positive charges repel each other through the electromagnetic force. Well, the strong nuclear force acts inside the nucleus of the atom and actually holds them together. It's stronger than the electromagnetic force. The weak nuclear force is also present inside the nucleus of the atom. It's what causes radiation, nuclear radiation. Objects to the inside of the nucleus will transform from one kind to another kind, cause the nucleus to change. That creates nuclear radiation and radioactive decay. Okay, electromagnetism, the strong and the weak nuclear force. We can describe all those quantum mechanically very accurately. In the 1950s, Richard Feynman was a physicist that described electromagnetism through quantum mechanics, and he calculated several quantities. He calculated what's called the gyromagnetic ratio of the electron to 13 decimal places, and it turned out to be correct to 13 decimal places. It's one of the most accurate predictions ever made and confirmed in physics. The strong and weak nuclear forces were also combined in quantum mechanics, and we now have a universal description of electromagnetism, the strong and the weak nuclear force in terms of quantum mechanics. But we still can't seem to get gravity to fit into the others. There's problems. There's mathematical problems that I'm not going to go into right now. But it has to do with length scale. The gravity works on large scales. It works on very long length scales compared to an atom. Quantum mechanics works on the scale of atoms. If you tried to describe what's happening gravitationally at small distance scales, like the distance of an atom, you get problems. There's problems in the way that that we mathematically describe general relativity when we try and formulate a small distance scale description. What happens is, and I'll just tell you the results here because this is a general audience, that the quantities become infinite. We get infinities when we try and calculate things. We get division by zero problems when we try and approach gravity quantum mechanically from a classical quantum mechanical approach. We need a new kind of quantum mechanical approach to describe gravity. And we know that this has to happen, that there has to be a way for us to quantize gravity, because at very, very small scales, called Planck length scales, we have a region of space and time that has to be described quantum mechanically, that affects when you calculate. Remember, quantum mechanics describes things on a small scale. When you describe things on a very, very small scale, and in fact, Planck length is approximately 10 to the negative 35 meters. When you try and describe something on that short of a distance scale, you discover that you can't do it without addressing gravity. The gravitational interactions, the space-time interactions have to be described quantum mechanically, but we don't know. Previously, we didn't know how to do that, but there's actually there's two possibilities, or there's two main contenders for trying to quantize gravity. One is called string theory. That's the old name. The new name is M-theory. And there's loop quantum gravity. These are the two big players in the field of quantum gravity. String theory predates loop quantum gravity. It arose originally. It wasn't the mathematics and the physics that describes string theory was developed in the 60s to understand nuclear physics. Later on, it was found that it could actually be used to describe fundamental particles like electrons and protons and neutrons and the particles that make them up. It solves some of the problems of quantum gravity, and the way it does it is it turns these particles, which we think of as points, it turns them into little strings. Some strings are open, some strings are closed, some form little loops in space, some don't, some are left open. But the vibrations of the strings give rise to the properties under string theory, under the hypothesis of string theory, that the way that the strings vibrate give rise to things like the mass and other properties, the spin, the charges. And the interactions of the four forces are basically the way these vibrations affect each other. The vibration of one string will affect the vibration of another string. This picture of strings that are vibrating is a way of unifying all the forces, the four forces, and to bring all the particles, all the 12 fundamental particles together into one type of object. It's basically a string that's vibrating. Quarks, some quarks which make up protons and neutrons. Some quarks are one vibrational mode of a string. Other quarks are another vibrational mode. Well, this wide range of particles can be described as basically just vibrations on a string. And the forces are the interactions of those vibrations, how one vibrating string would affect another vibrating string. One nice thing about this is when you try and describe a string using what's called classical quantum field theory, that you don't get these infinities that you would otherwise if the particle was a point particle. You're able to use a mathematical process called renormalization that allows you to keep the quantities you're calculating finite. You don't get these infinities and these division by zero problems. So with string theory, we were actually able to solve some of the problems of quantizing gravity that up to that point no one had been able to solve. There are some problems with string theories, and string theory became popular in the 80s, and it made a lot of predictions. It made a lot of brought a lot of mathematical ideas to the table. The problem is that so far, we haven't been able to test any of the predictions of string theory, because the predictions that we would make from string theory involve energy scales or length scales that are far too large in energy scales, too small in length scales to be able to test. We can't test these predictions because they would require, say, a particle accelerator the size of a galaxy. And so we have particle accelerators the size of cities. We can't build one the size of galaxies. That's the main problem with string theory. That's why it's sort of unsatisfactory that we can't have any predictions to test. Not yet, at least. We're told from time to time that string theorists will come up with ways of testing string theory, and they might not be telling us a lie. But so far, it hasn't been a good track record. They've done some very impressive things. They've solved theoretical problems, theoretical paradoxes and problems, but they haven't made a prediction that we can go out and say, look in a telescope or look in a particle accelerator and say, okay, this is either true or this is not true. So that's what science is. Science is about being able to test. If you have an idea, well, it can be tested. If your idea is untestable, what good is it? You may be right, you may be wrong. We'll never know if you can't test it. So that's what science is about, is testing. It's hard. String theory is a wonderful mathematical theory, but as far as the science, it's still premature to call it a science, in my opinion. Quantum gravity is a little bit, it's a newer way, a newer approach to quantizing gravity, but it's actually come up with some predictions that might be confirmed or rejected in the next decade, in the next few years. There actually, there's a telescope in space right now, a space telescope, that will be able to test some of the predictions of loop quantum gravity. What does loop quantum gravity do? Well, it's a sort of a very simple-minded approach to quantizing gravity. I'm not going to go into the mathematics, but I'll just talk a little bit about the developers of loop quantum gravity. It began in 1986. Abe Ashtekar was at the University of Pennsylvania, and he came up with a formulation, a way of writing variables that describe gravity in terms of quantum mechanics. Quantum mechanics uses a mathematics called operators, operator math. He was able to come up with variables that described curvature of space and time in the form that you could use quantum mechanical operators to understand. Later on, a couple years later, in 1988, Lee Smolin and Carlo Rovelli studied Ashtekar's variables and realized that they would solve an equation. This equation is called the Wheeler-DeWitt equation, and it's an equation that any quantum gravity theory would have to satisfy. And it turns out that the Ashtekar variables can be formulated in a way that satisfy the Wheeler-DeWitt equation. You see, the Wheeler-DeWitt equation is above Lee and Carlo there. Okay, so what happens here? Well, the idea, what Lee Smolin and Carlo Rovelli were able to figure out was that these Ashtekar variables will solve the equation, and they give rise, you can visualize this, the solutions give rise to little graphs, okay? And these graphs are called spin networks. Why are they called spin networks? Because the graphs are similar to objects that were studied by theoretical physicists earlier that were studying spins of particles. But we're not going to, I'm not going to worry about the exact name. It's just a graph, a special kind of graph that represents a solution to that Wheeler-DeWitt equation using the Ashtekar variables. And so you can think of space and time in this picture as points in space are basically vertices, and those numbers represent weights, or how the different points in space are related to each other. If you solve the Wheeler-DeWitt equation using Ashtekar variables for small spin networks, and the idea is that if you can zoom out these little spin graphs will start to look like space-time. And what does that mean? Well, if you can put mass in the system, that it would cause the numbers between these little points on this graph to behave in such a way that from a distance, it looks like you have a curved space, just like quantum gravity. And it turns out that they were right, that this is a way of describing the curvature of space and time in a quantum mechanical way. That actually space and time can be thought of as little atoms. They can be thought of as little discrete points. And they're related to each other through these loops here. That you can go around the loop, and that would describe the space around that point, how space is curved around that point, which is basically the gravitational field at that point in space. So I'm moving a little fast here. So what are some interesting results of this? Well, one interesting result of loop quantum gravity is when it's applied to cosmology. It turns out because there's a smallest distance. There's a smallest distance that you can make between these points in space. That's on the order of the Planck scale. That you can't have singularity. Singularities are single points in space where there's problems in physics whenever you get a single point in space. For example, if you look at our universe and you make it go backwards in time, it collapses to a single point where the energy density would be infinite, the temperature and the energy would be infinite. So if you can avoid going back to a single point, the energy density gets really large, but it doesn't go to infinity, which is good. If you extrapolate backwards in time using loop quantum gravity applied to on the cosmological scale, it turns out that the universe at the time that we call the Big Bang didn't go to a point. It went to a very, very small distance, but not to a point. And what happens, and you can go further back in time. What happens if you go further back in time? Well, if you go further back in time classically, you start to expand again. So our universe, this is a conjecture hypothesis, but it's a testable hypothesis, and that's important. We can actually tell, well, we should be able in principle to tell whether or not this idea is correct in a few years' time, hopefully. But if you go further back past the Big Bang, you go into a previous universe, a universe that actually collapsed and then bounced back. It bounced back from that little point that's not a singularity, but a little minimal Planck length distance that expanded back into our universe. Is this true or not? We don't know. But the nice thing is we can test it. We can test this idea. It's complicated, but the ramifications of this prediction are that if you look at the radiation, the background radiation of space, everywhere you look in space, there's microwaves. It's called the cosmic microwave background. That you should see certain types of fluctuations on large distance scales. If that doesn't make any sense, don't worry about it. It's something that the Fermi telescope right now is going to be able to detect, or at least we think it will be able to detect that. If the Fermi telescope does not see these fluctuations, then that means that probably this idea is falsified, that this idea is not correct. But it's interesting. It is interesting to think about that maybe our universe came from the previous universe. And I think a couple of you were at the talk I gave on cosmological natural selection. It's possible that our universe is actually the inside of a black hole in another universe. So that's another possibility, and so we can test that idea as well. This is some interesting testable ideas that we can look at. Another major, let's say, theoretical victory of loop quantum gravity is that we're able to predict the entropy of a black hole, which was a fundamental problem in quantum mechanics and thermodynamics. We had an idea that black holes have entropy. Stephen Hawking was able to derive a formula from thermodynamic principles, but we didn't know how to calculate the entropy of a black hole. Well, if you use loop quantum gravity to describe the surface of a black hole, you can think of it as made up of little tiny microscopic atoms of space. These atoms are actually space itself. They're not something in space. They are space itself. If you actually tile, if you just lay this little grid of atoms that actually are space, that make up space, over the event horizon of the black hole, the surface of the black hole, you're able to calculate the entropy, and it turns out to be exactly what we expected. This will lead hopefully to better understanding of quantum mechanics in extreme regions of thermodynamics. Okay, so what are some predictions? Well, I already told you about the cosmic microwave background. That's one prediction. If we are, say, the black hole of another universe, or our universe came from a previous universe, we can look for that. There's also the prediction of what's called dispersion, the dispersion of photons. High energy rays should travel slower through space than low energy rays due to the fluctuations, the quantum fluctuations at the individual loop scale, the Planck length. That means that basically violet light should travel through space slower than red light, because violet light has a shorter wavelength and red light has a longer wavelength, so it should travel slower. We can actually test, in principle, we can test this too. We're just looking for gamma ray bursters. These are objects very, very far away in the universe. They give off primarily high energy gamma rays. And if we can find enough of these, and we can measure, say, we can measure the light coming from these gamma ray bursters, we might be able to either confirm or reject this prediction. And again, it's nice to have predictions. If we have an idea that the universe works a certain way, well, we won't know unless we can test it. I said stay tuned for more. This is a very hot, active area of physics right now, theoretical physics. Okay, and that's it. Thanks for listening.
Dr. Julia will be free to take any questions if anyone has any. Anyone have any questions?
Does the Big Bounce theory predict anything about the universe collapsing again and then re-expanding and collapsing continuously?
No. The Big Bounce. So the question was, does this idea of a big bounce, that our universe actually came from a previous universe, either basically the whole universe collapsing, or maybe it's a black hole forming in that previous universe? So the short answer is no. It doesn't tell us about the fate of our universe. It might have something to say. Recently, some loop quantum gravity physicists have been doing calculations. Excuse me. That make predictions that show that dark energy should have a positive value. And if you don't know what dark energy is, in recent years, astronomers have discovered that the universe is not slowing down. It was thought for most of the 20th century that the gravity of all the mass in the universe is slowing things down. The gravity is sort of like a glue holding things together. And the universe is expanding. We knew that, but we thought it was expanding slower and slower. And someday it may stop expanding, and may start to contract again if there's enough mass and gravity to hold everything together. Or if there's not enough mass, it will continue expanding forever. But the one thing we didn't expect was to find that the universe is actually accelerating. It's not slowing down. It's not coming to a stop. Every year, the universe expands faster and faster than it was expanding the previous year. That discovery won the Nobel Prize this past year. The most recent Nobel Prize was awarded for the observation that occurred roughly 10 years ago, actually it's 1999. So a little over 10 years ago, they discovered that the universe is accelerating, it's expanding faster and faster. And so whatever's causing this expansion is called dark energy. And dark energy, the main contender for dark energy right now is something called the Cosmological Constant, which is basically a little bit of energy associated with each point in space. And loop quantum gravity has predicted the value that was measured, or at least it predicted a positive value for which would show that the universe is expected to expand faster and faster. So in a sense, loop quantum gravity has made I guess you call it a retro-prediction, because the statement came after the discovery. but it's nice to see that it's consistent with what's been observed. But in terms of the long-term fate of the universe, the Big Bounce doesn't say, as far as I know, and I could be wrong here, but I don't know of any connection between the Big Bounce that could have been the start of our universe from a previous universe or a black hole and the fate of our universe. Yeah, good question. Very good question. Any more questions?
So that actually means that the days are getting shorter, like we're speeding up. Because it feels like, time is getting shorter.
Okay, so we can definitely feel like days are getting shorter, especially when our professors assign us a lot of work
Yes.
and a lot of stuff to do. But no, this is basically the mechanics of the Earth. The Earth is tilted on its axis, and when it goes around the sun, we're in the northern hemisphere, and so we're tilted in our summer. We're tilted towards the sun, and so we have more daylight hours because we're more of the Earth is facing the sun than is facing away from the sun in the northern. So days are actually getting longer. They may feel like they're getting shorter, but they're actually getting longer right now just because of that. Any more questions?
Did we measure whether we are really going farther and farther away from the sun? Like you said, the universe is expanding.
Oh, that's an excellent question. So the universe is expanding on the largest scales. We say that the universe is expanding, and someday it's expanding faster and faster. Someday it's going to be expanding so fast that it could rip atoms apart, and then that's called the Big Rip. That would be the final phase of our universe's evolution, I guess you'd say, where universal expansion is going so fast that even atoms can't be held together, and it'll basically the universe will just be a big, huge, empty, ever-expanding point. It's sort of a depressing picture, but there's lots of interesting alternate possibilities, and it may just happen to a portion of the universe, and maybe local pockets will survive. But the question is, we say that the universe is expanding every year faster and faster. How does that affect us, say, on the scale of our solar system? Well, the answer is it doesn't affect us at all on the scale of our solar system. To notice this expansion, you have to actually look at huge distances, like the distances between, not galaxies, but galaxy clusters. Galaxies, our nearest large neighbor, the Andromeda galaxy, is about 3 million light years away. Even in that distance, you won't be able to measure any significant universal gravitational acceleration. To actually measure that effect only occurs on hundreds of millions of light year scales. Locally, the gravity of galaxies and clouds of gas and dust in our universe is much stronger. It's much stronger than the expansion rate of the universe. Now, someday this will change, possibly. Someday this will change to the point where galaxies will slowly start to be pulled apart from each other. And then within galaxies, eventually within galaxies. Now this is a possibility. We have no idea, pure speculation. But if things keep going the way they're going, the way they've been going for the last few billion years, then galaxies will slowly be pulled apart by the expansion of space, and then eventually star systems will be solar systems. At that point, we're very close to the end of the universe. But this would take a long time. If things progress as they have over the last few billion years, the calculations are that it would take probably many times the age of our universe, the current age of the universe, which we believe to be approximately 13.6 or 7 billion years, something like that. Many times that you'd have to wait a really long time, much longer than the universe has existed in its present form, at least, to start to see these effects. So it's nothing to worry about, and it's something that may change. We still don't understand what's driving this, although we have a very good idea. And loop quantum gravity and something called causal set theory is actually making predictions that are being confirmed in terms of dark energy measurements. So we might actually understand dark energy. Some physicists thought we'd never understand it. Some say it'd be 100 years. It may only be a decade, maybe a decade before we have a firm grasp on what's actually causing the universe to expand. But for now, all the ideas are speculation.
No, but I mean, even if it moves away in a minute quantity, which is not affecting your saying, but if we're talking a lot of heat and whatnot, and we are going farther away from sun, meaning further away from temperature, so we would face older temperature on Earth, not global warming.
Yeah.
Like theoretically?
No, this is happening on time scales. It's happening on very, very slowly. It's essentially unmeasurable. And it's not something that you could even probably begin to measure for a few billion years. Probably for actually more than that, probably tens of billions of years, maybe 50 or 60 billion years from now, you might even our little galaxy cluster will be alone in the universe because all the other galaxies will be pulled away from us beyond the speed faster than light. So by the way, there's a way to get through the universe faster than the speed of light. Don't tell anyone that. So the story is space can expand faster than the speed of light. You can't move through space faster than the speed of light, but space itself can expand faster than light can travel. But the Earth, you wouldn't notice this for tens, or maybe it's on the order of hundreds of billions of years. And so by that time, our star, the sun, would have become a red giant and collapsed and, become a white dwarf. So, there's something else that's causing the Earth to actually move away from the sun. Each year, the sun is just a little bit less massive than the year before because it's converting, every second it converts about the mass of Mount Everest, the largest mountain. It converts about the mass of Mount Everest into pure energy every second in the core of our sun. And most of that energy, it takes about 100,000 years for that radiation to work its way out from the core to the surface. But once it's there, it gets blown out into space. And so there's particles and energy leaving the sun all the time. There's a solar wind blowing away from the sun all the time. So the sun is losing mass. And because the sun is losing mass, each year it exerts a tiny, tiny little bit less gravitational force on the Earth than it did the previous year. So the Earth, and again, this is probably immeasurable. I don't think it is immeasurable. But each year the Earth is getting a little bit further away from the sun because the sun's gravitational field is getting weaker, but only by like 1 part in 10 or 100 trillion. But that's something. That's a different effect than the expansion of space itself. Very good questions.
Thank you.
Any more questions?
This is more about you than your talk, or this type of physics and things. Talk about what would attract you to an area of science where you know that you'll never really know the answer.
So, like string theory?
Yeah.
So that's a good question. I can only tell, like, from my personal experience. I like math a lot, and theoretical physics is a combination of sort of out there mathematics and very abstract ideas, trying to apply abstract ideas to concepts in physics and physical reality. Sometimes you get lucky and you come up with a mathematical model that makes predictions that you can test. Often, like the string theorists, it's a very beautiful mathematical theory. It does come up with predictions, sort of, but they're not realistic predictions. So it's sort of the roll of the dice. If you can join a field when it's starting to become mature. A lot of young physicists were sort of pushed into string theory. It was believed that any year they were going to be able to unify all the fields, the forces and all the particles, and basically have a single unified description of all of physical nature. But it turns out that there's a lot of problems. There's more problems every year that come up, mathematical challenges. And so we're still waiting for that prediction from string theory that can falsify it or at least confirm it. My personal opinion is I just like the math. So, and I don't mean to give the impression that this is my area of concentration. When I was an undergraduate in college, I did study this, but in graduate school I studied condensed matter physics, which is basically how atoms interact and on that scale. So those models definitely have consequences and predictions that we test and have, I guess you could say, closer to the applications and the consequences of those theories are a lot more immediate than what we're doing with loop quantum gravity and string theory. So it is a very interesting area of research that I follow, but I would never claim to be a loop quantum gravitist or string theorist.
Any more questions?
If the expansion of the universe is accelerating, does that falsify the heat death of the universe?
So the heat death of the universe refers to the fact that when everything reaches the same temperature, nothing else happens, nothing else interesting happens. To actually do work, I should go back to my head a little. If you, on the right-hand side here, you see there's a heat engine, and in order to do work, you have to have a heat, a temperature difference. Heat has to flow from a high temperature source to a low temperature source. If the whole universe is at the same temperature, heat's not going to flow anymore, and so you won't be able to do work. If you have a system where every point in the system is at the same temperature, you can't do work because heat's not going to flow. That's called heat death. The universe, the expansion of the universe is actually making the universe cool, if that makes sense. So it's actually it's approaching heat death asymptotically, or it doesn't contradict heat death. It's actually making the universe approach if we follow the predictions, assuming that the dark energy is a phenomenon that continues to happen, even though we don't know what it is right now. But if it turns out to be what loop quantum gravity is describing, or string theories, loop quantum gravity actually describes dark energy much better. Then it's going to make the universe eventually just get to be a very, very empty place, very low temperature, very cold place. And so the temperature is going to be pretty much close to zero everywhere. So it would be approaching heat death. Sorry, that sounds depressing, but the good news is that's not the only story. There's other possibilities, but yeah, it looks like right now we're approaching heat death through the accelerated expansion of the universe.
Any more questions? Yeah.
What exactly happens at the near infinite point of the singularity that makes gravity stop pulling and starts pushing again? And does that have anything to do with neutrinos?
So when you get singularities in physics, what that usually means is your math is insufficient to describe what's going on. It means that you need a better model. In quantum field theory, when you try and describe gravity using quantum field theory, when you go to very short distances, the problem is that the energies diverge as 1 over the distance squared. And so there's no way to, in a classical treatment, to actually make it stay finite. It just goes to infinity. As you go to very short distance scales, quantum gravity blows up. The energy densities go to infinity. Sort of like the ultraviolet catastrophe. Let's see, right? The ultraviolet, well, that's actually not a singularity, that's a divergence. But a singularity represents a point in space. It's a point in parameters, and parameter space, if you want to call it that, where the model fails, that it gives you infinite values. And at that point, you can't say, you can't make any predictions. The model's not giving you any information. It's so a singularity is generally bad. There's an area of mathematics called Catastrophe Theory that was popular in the 70s, and some research went on into the 80s. But you can actually catastrophe is basically studying what's happening around the singularity, just before your theory blows up. So by studying what's happening around the singularity, you can sometimes figure out what's wrong with the math or what's wrong with your model and be able to fix the model or maybe adjust it. Unfortunately, this doesn't work with quantum gravity. So the short answer is singularities. We don't like singularities. When we see singularities, it means what physicists usually think is, well, I need a better model. I need a better something to fix this. So. We don't see infinities in the physical universe. Good question.
Any more questions? Nope. Great. Thanks everyone for coming, and let's hear it again for Dr. Bernoulli.